Welcome everybody to the fourth monthly webinar series of our Nutrient Management Spear program called Lunch with the NMSP, Food for Thought. Today's webinar is about practical on-farm research and data-driven decision making. My name is Corinne Ketterings. I lead the Nutrient Management Spear program at Cornell University. And for those of you less familiar with our program, we have as motto for our program to ask ourselves relevant questions, conduct sound science for agriculture profitability, and protection of the environment. We partner with a lot of people in the state of New York. That includes farmers, certified crop advisors, nutrient management planners, Cornell public extension specialists, soil and water district staff, other universities, state and federal agencies to meet this mission of trying to improve the profitability and competitiveness of New York dairy, livestock, and cash grain operations while also maximizing environmental protection. Our program has 6 focal areas. The first one is our land grant responsibility for development and implementation and support of science-based guidance for nutrient management for New York. The second one listed is soil health and climate resiliency. We work on precision agriculture applications, and that is what today is about also. We also work on dairy sustainability, on-farm research, which you will hear more about today as well. And we have a component of student engagement, and that's important for our mission and trying to engage as many students as we can, both within Cornell and outside, to join us for internships. In terms of internships and student engagement, we have several opportunities for students to join us this summer. So if you are a student interested in getting involved in some of our projects or know of students that might be interested, feel free to let them contact us. We celebrated 25 years of existence last August with our entire team. And so we're in our celebration year, and we thought we give ourselves some extra work. So as part of our celebration, we started the monthly webinar series. This is the 4th one today. We've had 3 other ones. The start of it was in December with a session on dairy sustainability, key performance indicators. That was followed in January with a webinar about adaptive nitrogen and phosphorus management. Last month, we talked about using yield monitor data to turn that into actionable information. And all of these webinars are now posted on our YouTube channel. You can get to that YouTube channel by searching for Animal Science YouTube, but also by going to our events page on the Nutrient Management Spear Program website. That is also the place where you will find links to signing up for the next webinar. Our next webinar is on April 3rd, and the topic for that webinar is the value and the power of manure. So if you want to join for that webinar, make sure you register. And if you go to the events page on our website, you will find the link there to register. Before we dive into the webinar for today, I wanted to share some exciting news, at least for us, that we were selected as a Nutrient Management Spear program for the 2026 CALS Outstanding Accomplishments in Extension Outreach Award, which ceremony happened last Monday. You see some pictures of that. The work we do and the work we've done over the last 25 years recognizes the contributions of not just our current team, but also our past members and all the partners that we work with, the farmers, the farm advisors, the consulting firms, the state agencies, etc. So big thank you to all of you that have in some way or shape contributed to our success as a Nutrient Management Spear program over the past 25 years. Today's webinar, Lunch with the NMSP, Food for Thought, focus on practical on-farm research for data-driven decision making. We will have CCA, continuing education credits, 1 credit in professional development, and we'll post the QR code at the end of the session today. The webinar today I'll be delivering together with Suba. Suba is a postdoctoral researcher in our team. And we also want to recognize Juan Carlos Ramos-Sanchez, our on-farm research coordinator. He is not with us today for the presentation, but he will be a lead presenter in the webinar on April 3rd, The Value and Power of Manure. We also want to recognize many of our past members that work with us on precision agriculture, and they are listed here. This, what we present today, represents a continuing involvement of knowledge that we gathered over the last 25 years with a focus on precision ag. So where does the webinar today fit in? It's part of our on-farm research. We're going to be talking about some approaches to doing on-farm research, part of on-farm research network. We lead the New York On-Farm Research Partnership in the College of Ag and Life Sciences. And again, you'll see our model here, relevant questions and sound science for agriculture profitability and protection of the environment. The whole idea behind the On-Farm Research Partnership is that we partner with the farmers, with our colleagues at ProDairy and Extension, our consulting firms, other farm advisors and agencies, and that we aim to establish a statewide research partnership that enables us to pose those relevant questions and get those answers and get questions answered efficiently. So building of databases over time, aiding in the development of science-based guidance and implementation of both on-farm and whole farm root management practices that meet that goal of agriculture profitability and protection of the environment. You scan the QR code here, you come to a list of our currently ongoing active on-farm research projects in 2026. We partner throughout the state. Anybody, doesn't matter if it's Northern New York, Western New York, Central New York, we are interested in partnering with everybody out there working on field crops and nutrient management related topics to advance our mission here and to help farms implement more science supported decision making on their operations. We want to foster two-way learning, so learning between farmers and us on campus with farm advisors involved, a two-way street, so that we identify the right priorities of research to look at, on-farm research to pursue, and so that we see how things work in the backyard of the farm itself, so on the farm itself. We want to create a network of community engagement and peer-to-peer knowledge sharing as well, with farms pulling their data together and learning from each other. We want to give farms in this network an active role in developing profitable, environmentally sound management practices and help them make those data-driven decisions. This is a summary of our on-farm research partnership. In 2025, farms participate in all sorts of different ways. It could be regular agronomic trials on farms. It could be data sharing for generating yield zone reporting. We have over 100 farms participating in whole farm mass balances. Many of those farms are also participating in dairy sustainability indicator assessment, carbon footprints, and things like that. Some projects do not involve a lot of farms, are more concentrated on a couple of farms, like the Dairy Soil and Water Regeneration project that we will be talking about later in the year. Others have larger participation. Altogether, 350 touch points in terms of on-farm research in 2025, and we're looking forward to expanding beyond that even in 2026. What we wanted to talk about today in the webinar series was more the agronomic on-farm research components. So conducting trials at the farm itself. And we're going to zoom in on two common designs, the randomized complete block design and the split block design. And then after I talk you through those two, I'll hand it over to Suba, who is going to talk specifically about a new approach that we launched a little while ago. That's called the single strip spatial evaluation approach, a technology-driven approach to doing on-farm research. Let's start with the first one, the randomized complete block design. This design has been in place for a long time. It's a design where we take a number of treatments that we want to compare. And the example here is maybe we have a seeding rate study where we have a particular rate A. We might have a rate B and a higher rate C. So 3 different rates in this example, treatments 1, 2, and 3. And we put those in plots next to each other, 1, 2, and 3, within a block. And then we do the same thing. We repeat that, but we shuffle the treatments around. So now it's 2, 3, and 1 next to each other. And then we do that a third time. And now we have treatments through 2 and 1. So we randomize the 3 treatments within a block. And we have 3 blocks in this example. 3 blocks is the bare minimum. Most of our trials where we use this design, we shoot for at least 4 replications if we can, if the space is there. It's important that the treatments are randomized within a block. And it's also reported for this design that the experimental units are as homogeneous as possible. And then when we do the blocking, we put the 3 treatments within one block next to each other, that differences, the pre-existing differences are as small as possible. So homogeneous experimental units within blocks. If we can trust that within this block, the initial conditions were all the same, then I can also maybe trust the results that say that one of those treatments gives better yields, right? So really important that the experimental units in a design like this are as homogeneous as possible. Blocking is done to achieve those homogeneous experiment units and to be able to get more power out of the design to draw conclusions from. Type of research questions, could be all sorts of different questions. Here's a couple of examples. The first one is, for example, a population density question, like what is better, 28,000, 30,000, 42,000, 40,000 seeds, whatever the numbers are. I could do a comparison of species, like if I'm working with cover crops, what's the difference between rye, clover, and wheat in terms of biomass or in terms of their impact on the next crop. I can do the impact of tillage practices. Maybe we compare strip tillage versus chisel plowing or no-till. We can do manure studies. Does manure injection improve yields? Things like that, yes or no questions. We can also do rate studies. In this example here is nitrogen rate. We can ask ourselves questions with this design, like if I lower my rate by 40 pounds, do I get the same yield or not? We could also do rate studies where we try to determine an optimum rate. But in that case, we need to have at least 5 treatments, 5 rates to be able to do that. Here are some examples. On the left is one of those rate studies where we have plots from left to right. There's 15 plots here. We see 0, 50, 100, 150, 200. That's block 1. 5 treatments in block 1. In block 2, we have the same 5 treatments, but they're differently organized. Now it's 100, 50, 0, 200, and 150. And then we have the last block where it's yet again randomized, 50, 20, 200, 0, 150, and 100. So that's a complete block design, 3 blocks in this case. It's randomized within the blocks. And this is set up in such a way that the strips can be harvested with farm equipment. So this is large-scale plots going through a field. Because we have 5 treatments in here and 3 reps, we have 15 plots. 3 reps is the absolute minimum, 4 would be better. Picture on the right is also a randomized complete block design. Here we have 5 treatments, 5 nitrogen rates in a block, and this one is 4 times replicated. So the first set of 5 is 1 replication or 1 block, the second set is 1 block, the third set is a block, and the fourth set is a block. So this is 4 replications of 5 treatments, gives me 20 plots. And I also put up this picture because I wanted to point out that these randomized complete block designs are not equipment specific. If you have farm field equipment and you want to harvest long strips, totally fine. You could also do smaller plot scale. This is 10 by 10 plots, where we did nitrogen studies for the winter cereals at Green Hub. to grow it as a double crop for forages, where you see a 10 by 10 area as the experimental unit with hand harvest of those plots. Both of those are possible. You don't need yield monitor equipment for this design. Some of the results that you might get, you'll see the typical charts where there's listed A's and B's or to show if things are different. And this is just an example. Don't take this literally. It's just an example of the type of results you might get. 3 different average yields with indicated whether or those are statistically different. As I mentioned, the design can also be used to determine optimum rates. But to determine an optimum rate, you need a curve. You need a response curve like the one here on the right in terms of fall uptake of nitrogen of a winter cereal scenario. The range that we're looking for here, the middle value of the 5 rates is what you expect to be optimal. You want 2 rates that are over, that are more than what you think you need, and 1 rate that is a 0 for a nitrogen rate study. Right. So 5 in a minimum for most of our trials. We do 6 rates to determine a curve like this. A randomized complete block design can be used for that, but as you can see, if you have 5 rates and you need 3 replications, immediately have 15 plots to work with. Pros and cons. Pros for the randomized complete block design allows for direct comparison between several options, different treatment types, as I mentioned before. It can be done with farm scale equipment, but it's also conducive to small plot work and hand harvest. So it doesn't eliminate anybody. Anybody can do this type of design. The negatives, it's important that the experimental units are as homogeneous as possible. Those of you working in New York know that this is occasionally well, maybe more than occasionally, can be a challenge to find a homogeneous field. It's somewhat complex to set up. It needs some thinking. It needs some design. It needs a lot of plots and space if you have multiple comparisons. For example, the rate studies, if you have your treatments, let's say you have 5 treatments and you do 4 reps, you have 20 plots. You have 5 treatments, 3 reps, you have 15 plots. It quickly starts accumulating. It will most likely slow you down at harvest with alignment of equipment, with making sure you harvest the right plots. And it is limited in statistical power. All right, with that, we're going to shift over to the next common design that we currently also work with. And that's a split plot design. So split plot design is where we have main treatments that are full strips, and we have subplots that divide those full strips into smaller plots. This is the design that we use for our value of manure studies that we will talk about on April 3rd. The example here is from that project. We have 3 strips, the blue ones, where manure is applied, and then 3 strips in between where manure was not applied. And this is done in 3 blocks, so where 2 treatments are with and without manure in block 1, block 2, block 3. 3 times replicated in this example. Again, 3 is the minimum, 4 is better. That is the main treatment. Has the obvious advantage that you don't need to zigzag through a field to apply the manure. You can just apply it to those strips as the main treatment. And then the subplots on the right, we take those strips and we divide it. And in this case, we divided it into nitrogen sidedress rates, ranging from 0 as the control to 175, with 175 being way over what we thought we needed for this location. So the type of research questions that this split plot design can help us answer and makes easier to answer is allow a combination of treatments. So with and without manure, what is the optimum N rate? For example, for the manure plots that I just showed you. This is also the design that might help us answer questions about biologicals and their ability to lower the optimum N rate. So you need the multiple N rates to create a curve, and you can do that with and without the biological. So instead of the manure treatment, maybe have biological as the treatment in the full plot, and then the sidedress nitrogen as the subplot rates. It's a lot easier to answer those questions with a split plot design than with the randomized complete plot design. This is an aerial image of that example with split plots, three strips where manure was applied, and three strips where it wasn't. And then the subplots are the side dress rates. Just an image of what that could look like. For this split plot design, the picture on the left is a larger scale design. The picture on the right is small plot. And this is also a reminder that this design is not limited to people that have the large scale equipment or yield monitors. This can also be done with a hand harvest. In the situation on the right is one of the value of manure studies. This was a hand harvest plot with smaller plots for the strips that did not get manure, larger plots for the strips that did get manure. Both of these options are totally valid. What we do with these rate studies is try to determine an optimum rate with manure, in this case the brown line, versus the optimum rate without the manure, in this case the gray line. And then we compare those optimum values. In the case of the brown line with the manure applied, the yield was 29.1 at an optimum N rate of 56. When manure was not applied, the yield was 28.5 and an optimum N rate of 114. So that allows us to conclude that the manure supplied 58 pounds towards the nitrogen needs of that crop. That's the way we come up with optimum N rates studies, and the split plot design really allows us to get there. Pros and cons. Pros, it allows for clear testing of an optimum response at two different situations, with and without manure, with and without a biological, with and without strip tillage or stuff like that. The trial setup for the whole plot treatment is simpler. One long strip of manure instead of having to separate it out over smaller plots. The subplots are smaller, they take less space, and it can be done with farm scale equipment, but it can also be done with a hand harvest. On the negative side, same thing as with the randomized complete block design, it's important that the experimental units be as homogeneous as possible. Complex to set up and analyze statistically, so maybe not something you would do by yourself, but get some help with. It can quickly generate a lot of plots depending on how many levels you want to evaluate. It could slow you down at harvest, and it has limited statistical power, just like the randomized complete block design. So we've shown some characteristics of the two common designs that we're currently actively working with in some of our own farm research. That's not to say there are not other approaches. It's just to pick two ones that are commonly used. And with that, I'm going to hand it over to Suba to talk about a new approach that we designed, the single strip spatial evaluation approach.
Thank you, Corinne. Am I audible?
Yep.
Okay. I'm gonna just test the slides. Okay. Hello, everyone. I'm Subhash Srinivasakan, and I'm gonna be talking about the single strip spatial evaluation approach. I've been working with this for over 3 years now. So yeah, let's get into it. So some of the common cons that we see with the traditional design is that the field needs to be homogeneous as possible, which means that there should be no spatial variability whatsoever, and we need to keep that at the minimum. And if you had looked at the designs, it's complex to set up. So the nature of the design sort of like slows you down during the application and also during the harvest times, which is one of the busiest, times for the farmers. So with these two traditional designs, at the end, you would get average yield per strip or per subplot, which helps you to compare the treatment and the control. And because of the amount of data that you can get from these trials, there's limited statistical power associated with it. So our goal was to sort of like eliminate these bottleneck for on-farm research, and also to have simple, straightforward, and easier to adapt sort of design. So with the farmers in New York, you know, adapting this yield monitor sensors. So they use these yield monitor sensors for corn grain, corn silage, and also for soybean recently. So we were able to realize this goal of ours to introduce something simple, straightforward, and easier to adapt. So we've been collecting yield monitor data since 2007, and we have about over 500,000 acres of yield data across about 68 farms, which are cleaned and processed by the Nutrient Management SPEAR program. So then we use this data, this wealth of data that we already have, and introduce something called as the single-step spatial evaluation approach, C for short. So this is how an yield monitor data would look on the field. So this is the harvest data that's been collected, and each point that you see is a harvest data, and that's specific to that location. So every point has a latitude and a longitude attached to it. So it's a spatial data. And as you can see, there's this yield variability, and we are going to be taking advantage of this yield variability that we see here on the map. So let's look at a scenario where we are implementing a randomized complete block design on this field. So as you can see, it has taken up more space of the field, and it has about like 4 blocks with the replication of like the control and the treatment. So here, as you can see, it could be difficult. It is difficult for sure during the time of harvest to sort of like harvest the data per strip and then account for the yield and to compare with the control. So imagine if these strips can be replaced by just one single strip, where the treatment that's in question can go into this strip, and that's evaluated with the compared with the rest of the field that's in orange. So here the whole field other than the treatment strip becomes the control. So I have sort of overlaid the yield monitor data to show the number of yield data points that's inside the treatment strip. So the yield data sort of now becomes a testament to see if the treatment that was implemented impacted the yield inside the strip when compared to the data around it. So this is the whole concept of the single strip. So it's easier to implement. The only thing that happens is implementing this strip, and rest of the operation happens as usual. So the harvest, the chopper or the harvester moves around with the yield monitor data and then collects the yield data as usual, and we would be able to sort of overlay the strip on the yield monitor data to see how the data has impacted or not. So what are the C requirements? The first one is, of course, the yield monitor data. And the second one is the spatial variability, called as the yield stability zone map. So let's sort of dig deeper into how we come up with this yield stability zone map. Imagine if a field has yield monitor data for over 3 years. And now these data points are then collected, are pooled into are, are pooled for creating 4 zones. So this is just not coming from one field, but this is coming from all the fields in a farm that have at least 3 years of data so that we can see a spatial pattern in the field. So it's then divided into 4 categories using the farm weighted mean and farm weighted standard deviation. So here, the first zone is zone Q1, which is the high yielding and consistent zone. So it's consistent because it has lower standard deviation and the yield is more than the average, the weighted average yield. So we have zone Q4, which is the low yielding zone, but consistent because it has lower standard deviation. And then we have the Q2, which is variably high yielding, and Q3, which is variably low yielding. If all these colors sort of confuse you, just remember the green and the yellow, the green and the red. So the green is good, which is the consistently high yielding, and the red is bad, which is the consistently low yielding. So the goal for any field in a farm is to move the data from Q4 to Q1 by implementing a product or a management practice that we could test with the single strip analysis. So I mentioned that we have about more than 500,000 acres of yield monitor data. And from that, for corn grain, we have about close to 25,000 acres of yield stability zone maps that we've processed. And for corn silage, we have about 46,000 acres. And soybean, which is a relatively new data, we have about 5,000 acres of yield stability zone maps so far. So we also have an agronomy fact sheet in our fact sheet series that sort of like takes you through the steps that we just discussed about the farm weighted mean and the standard deviation into getting these 4 zones. So you could access this if you want more details on this. Okay, moving on to C results. Now that we have the yield monitor data, the yield stability zone map, in addition to these two important things, we also collect the temporal average yield, which is like the average yield of that particular field over the years. And then we also input the latitude and the longitude, which is the spatial information that we can derive from the yield monitor data. So we put that into a spatial model. So I'm not going to take you through the spatial model, but I'm going to share you the results that we report back to farmers. So the result one is sort of for visualization is not coming from the model. So this is looking at the zone distribution in the field versus strip. Say the outer ring here sort of shows the zone distribution for 4 zones in the field. And then we also have the zone distribution for the strips. So we can see that there are 2 additional strips on top of the treatment strip that I earlier showed. So this is sort of like the representation of the rest of the field. So these control strips are delineated during the time of analysis, and it is not implemented when we are implementing the design itself. So there's only one single strip going into the field. So here for this case, we see that even though we have 4 zones in the field, we have about only 2 of these zones, the high yielding zones Q1 and Q2 in the strips that goes into the analysis. Moving on to the next one, this is the primary output of the C analysis spatial model. So we have that in the form of a confidence chart. What this chart essentially tells you is that if the treatment that was implemented impacted the yield or not. And it tells you the story for across all the 4 zones, starting from Q1 to Q4. So we saw earlier that we did not have the zones Q3. We did not have enough spatial points for Q3 and Q4, and therefore you see the NAs for Q3 and Q4. And yeah, let's move on to the high yielding zones Q1 and Q2. So the green box that you see here shows the yield categories for the yield benefit. So the treatment that was implemented benefited the yield when you compare to the control strips. So the numbers that you see inside the confidence chart are the confidence percentages that are categorized into 5 classes, starting from highly confident to not confident. So when you look into the zones Q1 and Q2, we do see that the product helped more with the zone Q2, as we see that we have about 94%, which is high confident that there is going to be an yield bump between 0.5 to 0.75 tons per acre when the product is implemented. As compared to like zone Q1, which also benefited in the yield, but not as much as Q2. As we see, there's high confidence between 0 to 0.5 tons per acre. So there is an yield bump, but not as much as Q2. So this sort of like tells us that the implementation of the C across zones makes sense because it not just answers if the product works or not, rather it also answers where this product works in the field. Okay, so I'm going to be showing a short demo of the C tool that we developed. A little bit of background as to why we developed this tool. As I mentioned earlier, we've been sharing the yield monitor data, we've been sharing the zone maps, and we also been sharing the temporal average yield back with the farmers each year as farm reports. So they already have access to this data themselves. So when they have a single strip implemented in these fields, they do not have to rely on us for generating the analysis for them for the single strip, but rather they could use the data that they already have and run these analysis themselves. The tool is made in such a way that the spatial model sits inside of the tool, which will generate the important results, the confidence chart and the zone distribution, while it also interprets the results and then puts them into like a format, a report format, and then you can download them as a PDF. So I'm going to be going into the tool demo, and not going to be talking unless if it's required. So I'll let you enjoy the demo. It takes you through the strips, the field that has the strips in it. This is the yield stability zone map. And here we have majorly the low yielding zones, Q3 and Q4. This is looking at the temporal average yield. And now we are importing the current yield monitor data for 2024 when the treatment was implemented. Here I'm just switching the layers off for you to see the yield monitor data more clearly. Now, this part of the tool is not required for the model to run, but it helps with the information being fed into when the report is being created. This is the zone distribution plot. And then we have the confidence chart. So this is the section where it auto-interprets the results from the previous tab and also shows how the report would look before you download it. You could also edit if you see something that's not right, or if the language you want. Then you can download them as a PDF report. So the tool also has a user guidelines in the about section where it takes you through each step and gives you a detailed instruction as to how to use the tool. It also has interpretations for the confidence chart. Okay, now that's done. Let's move to, okay, before we move to the next section, we have this agronomy fact sheet on creating the strip shape files for the single strip spatial evaluation. So we realized that the farmers have all the data that they need for running this spatial analysis, the C analysis, but they were lacking the strips. So originally we used to create the strips for them and then run the analysis, but then this fact sheet would help them to create these strips, and it also comes with a video demo that will take them through the fact sheet. Okay, now that we've seen how the C can be helpful in using the yield monitor data, this is the most important part as to what not to do when implementing the C trials. So the first one is obvious. Do not select a field without the yield monitor data or an yield stability zone map, because currently the single strip spatial evaluation approach relies on the yield monitor data. So if you know that the field is not going to have either of these, then it would be wise to not select that field. Two is that the treatment strip should not be close to the field edge. We put that here because we have seen a lot cases like with the fields that we've worked with, where the treatment strip is close to the field edge, where the headland effect could influence the treatment, and it could not reflect the actual result of that treatment. So similarly, when you leave enough space for the control strips, we should make sure that these control strips should also not land in the near the headland area for the same reason. So you might ask, what would be the ideal location for this treatment strip? So in most cases, we found that the ideal location was in the middle of the field, where it has enough space for delineating the control strips on either side during the analysis. We also have a fact sheet on the C itself, which talks about like what kind of treatments you could implement, and also takes you through different steps, starting from what equipment you require, how to implement the strip, what the size of the strip should be, and how the data should be collected, and about the statistical analysis as well. So I have a few examples to show you from the C trials that we've done. So so I wanted to show you this example because it's very rare that you have all the four zones in a field, and say on these zones being represented in the strips too. So here we have a perfect example of all the four zones present in the field and as well as in the strip. And here we see that with this product being implemented, it really helped the low yielding zones Q3 and Q4, and not so much for the high yielding zones Q1 and Q2. In fact, this product did have somewhat confidence in having an yield loss for these high yielding zones. So it sort of emphasizes the fact that if this treatment was to be implemented as a blanket for the whole field, without the zones being present, there would be a net benefit, but we wouldn't have seen these differences in the zones for high yielding and the low yielding if these yield stability zone maps weren't present. And you could also have multiple strips in the same field where you could test two different products. So product A could go into one strip and product B could go into another strip. The only thing that you have to keep in mind is that to have enough space for the control strips. So here we have about 3 control strips, one being in the middle and then 2 on the other side. Okay, so we've done about like 20 C trials in New York so far, and these are some of the cases that we tested. So we've done population studies, we've tested the need for pop-up fertilizer, we have tested different citrus nitrogen rates, manure trials, and also biologicals. So this is a quote from a farmer that we worked for over 3 years, where they emphasize the practicality and the use of this approach, which makes it a welcome trial on a busy farm, which was the goal for us while creating this single strip spatial evaluation, to make it as simple, straightforward, while being statistically powerful. Okay, so far we've seen that the sea being heavily reliant on the yield monitor data, and we wanted to move away from uh, being that reliant. And we also started exploring the potential of the remote sensing platforms. So we've been looking into high resolution satellite images from the Planet's lab to look into how we can create those yield stability zone maps. And I've been collecting multispectral drone images over the summer for the past 3 years during key growth stages to look into how I can recreate the yield monitor data. So the yield monitor data here will be the ground truth for me. So these are some of the work that's ongoing. Now over to Quinn.
All right. So in this webinar, thank you, Subaho. For in this webinar, we've looked at basically three designs, two of which are very common designs that we use for various of our on-farm trials as well. The third one, the C approach, is a new approach. Randomized complete block design allowed us to compare multiple treatments, split plot, brought in the main treatment, the main one big treatment, and then subdivide the plot to be able to answer some questions. Some rate studies are really good for that. The C approach is the one that will require yield monitor data and zone maps. So farms with zone maps will be able to, and yield monitor capacity will be able to do these trials. And it really simplifies on-farm results, makes it much more simpler to implement straightforward harvests. You don't need to line up anything anymore, as long as your strip is twice the harvestable width. Um, this will be on-the-go harvest, and then the yield monitor data can be analyzed using the new tool that Suba developed. The C approach is also unique in terms of it takes into account the spatial variability. And we have that in every one of our fields. So the field does not need to be homogeneous. It can also be used, when we use the C approach, we can learn how to manage yield stability zones within a field. So the C approach can help you answer the questions, do I need to put more seeds in the ground in high yielding zones or less? Do I need to put more nitrogen in those zones or less? Questions like that can simply be answered using the C approach without slowing the farm down, as the only thing to be implemented is the strip itself. Food for thought is our subtitle for the webinar series. Here's some things to think about. The power is in your yield monitor and in the data that it is collecting. We can make use of the data we already have to design smarter and simpler on-farm research, gaining knowledge on the go, taking away a barrier to conducting on-farm research at the farm level. As I mentioned, we have our New York On-Farm Research Partnership. We invite anybody interested in conducting on-farm research to connect up and become part of it. If you have yield monitor systems on your choppers or combines, and you have the data and you want to know what adjustments you want to and need to consider based on the zone maps, we're happy to work with you. We're actively looking for people who want to explore the single strip approach this year, learn more about how to manage based on yield stability zones. It would be great if there's a group of farmers that want to work together on a particular question and all do the same type of strip, but we can also work with individual farms. And Suba has shared a couple of examples of that already. With that, we've come to the end of our webinar for today. Webinar number 5 is on April 3rd, the value and power of manure. And I want to share this slide as well and thank our funding agencies. We work with a lot of people. This development into what we currently have for approaches, including the single strip approach, is building on many years of field trials and analysis sponsored by many of the organizations that you see on the screen here. With that, we're going to open it up for questions.